In the last lecture, we introduced the stress energy tensor, and in the previous lecture before that, we introduced the whole notion of continuum mechanics. So, what happens in continuum mechanics? I will just summarize the last two lectures first. Remember, for a discrete system, that means you have finite number of particles, you can label the particles as 1, 2, 3, 4. But when we have a continuous system, then of course, we have infinitely many particles or at least sufficiently large numbers, so that you do not want the motion of the individual particle, in which case instead of numbering them as 1, 2, 3, 4, I now use a continuous variable to index each particle, and that is how the individual field variables now become a continuous, or individual generalized coordinates, they now become the field variables. Okay. So, remember the typical example of the rod, in which you have elastic rod, in which you have parts of that particular rod, which can be thought of as atoms and molecules, are getting displaced from their equilibrium position, and the displacement, if you think of this as a discrete system, would be generalized coordinates indexed by the integers, but when you have continuum system, I will index them by a variable called as x. Remember, because the rod is also placed in our physical world, it makes sense to talk about individual points of the rod by the same variable which I use for the coordinates in the ordinary space. Now, when you go to the bulk case, of course, the same thing can be extended to 3-dimensional case, and the individual displacements eta now become a function of x, y, z and t, and that is what we called as field variable. And then we extended the entire Lagrangian formulation from the discrete system to the continuous system. In today's lecture, what I am going to do is do the continuum system, but with a Hamiltonian formulation, and also probably introduce Poisson brackets. You see, in case of particle dynamics, the Hamiltonian formulation or Poisson bracket formulation provided great insights into the nature of the problem itself, or the structure of the classical mechanics. And it also of course allows you to do great many generalization to the more sophisticated theories. But in case of the fields, or in case of continuum mechanics, we will find that probably it is not such a great idea to use Hamiltonian formulation. I will come to the individual problems that are associated with it, but we will anyway go ahead and construct the Hamiltonian formulation. Okay. So, let me start first, of course, by looking at the discrete system, and just like in case of Lagrangian, I took a discrete system and took its continuum limit. I will do the same thing here to derive the Hamiltonian formulation. Okay. So, same example, the rod there which has a length L, it obeys Hooke's law. Now, I am going to think of this as a discrete system of n individual masses, each of this mass having mass small m, and they are placed a distance a apart from each other in a linear fashion, okay. And they are connected by identical springs. The individual neighbors are connected by the individual springs, and then there are these vibrations or displacements of individual particles along the line. I am considering only longitudinal displacements here, but they are denoted by these displacement vectors, okay. Fine. And then from here we constructed the Lagrangian, okay. Now, I want to do the same thing for finite system. I will write down the Hamiltonian of the system. So, for the ith particle, I will look at the conjugate momentum pi, or define it as del L over del eta I dot. But remember, the way we wrote Lagrangian there, I wrote it as finally summation over A times Li, where Li was defined as m by A eta I dot square minus the potential energy term. Okay. Now, when you took the continuum limit, your Li becomes the Lagrangian density, and the summation over I with A will become integral over dx, integral over the continuous space variable. Then calculate the Hamiltonian for the finite system or the discrete system. That would be just sum over I pi eta I dot minus the Lagrangian. Now, I will write this in terms of del Li over del eta I dot. Remember, pi was partial derivative of L with respect to eta I dot, but eta I dot appears only in one term, that is Li. So, eventually that derivative will be partial of Li with respect to eta I dot. So, I will write that, and then the Lagrangian as summation over individual Li multiplied by A. And now use the same trick. Go ahead and take a continuum limit at this point. Remember, the continuum limit was taken such that the number of particles go to infinity, mass of each particle goes to 0, the interatomic or interparticle separation goes to 0, keeping the density constant. So, m by A remains constant, and similarly the spring constant goes to infinity, but the product of k at A remains finite and is equal to the Young's modulus. Fine. So, here take the same limit, and when you take the limit, summation over I multiplied by or A, this one here together with summation will become the integral. Li becomes the Lagrangian density. So, Li here and Li here will be replaced by the Lagrangian densities, and eta I basically becomes the field variable eta of x, and then I can write this like this. And now it has a structure of Hamiltonian density. Okay. So, what we are going to do is just like Lagrangian density, now I will add few more ideas which are momentum density. Of course, in case of stress energy tensor, we have already talked about momentum density, but now define the momentum density and denote it by letter pi as limit I going to 0, the continuum limit, and pi divided by A. So, you take sum of all the momenta in some neighborhood, divide by the length or volume of the neighborhood, and then you get this momentum density. And in the same way, define the Hamilton density. So, Hamiltonian density will be pi eta dot minus the Lagrangian density. And now we have got the Hamiltonian. What I want to do is, remember, in case of Lagrangian formulation, we try to derive a set of equations or the formulation which almost exactly looks like a particle dynamics or discrete system, but it is in terms of the Lagrangian density or energy density and momentum density. So, same way the Hamiltonian case also, I would like to try and see if I can get the set of equations, the equations of motions, which look almost like or exactly like the discrete systems. Fine. Let us try and see if we can do that. So, when you go over from Lagrangian to Hamiltonian in finite systems, then we take a Legendre transform, and when you take the Legendre transform, of course, del H over del P becomes q dot, del H over del Q becomes minus del L over del Q, and the partial derivative of H with respect to time is also equal to minus of partial derivative of Lagrangian with respect to time. So, these are, remember, H, L, all these quantities which I am writing here, they are Hamiltonian, the total Hamiltonian and total Lagrangian, and we want to see if I can derive similar equations for the Hamiltonian density. The equations of motions were given by qi dot. So, I will add that qi dot here dot, and Qi. These two equations of motion. And you will see now the difficulty that we face here when we actually try and derive these equations. Fine. The final equation would be dH by dt is equal to partial. So, what happens is, if the Hamiltonian is independent of the time variable, then the Hamiltonian itself is a conserved quantity. Unlike the Lagrangian, remember, if the Lagrangian is independent of time, then it is not the Lagrangian which is conserved quantity, but it is the energy function. Okay, fine. So, now immediately we will generalize this to 3-dimensional case, in which case the field variable eta will get replaced by eta sigma, 3 component field, okay, maybe vector in character or whatever it is, but it has 3 components there. Similarly, the momentum also will have now 3 components, and I will denote it by pi sigma, which is partial derivative of Lagrangian density with respect to eta sigma dot, right. And I will write here the Lagrange's equations. Remember, it was d over dx mu of partial derivative of Lagrangian density with respect to eta sigma mu minus partial of L with respect to eta sigma. And remember, there is a summation here over mu. And how many such equations? For each row, there is one equation. So, rho can take values from 1 to sigma can take values 1, 2 and 3. Fine. So, let us start by defining the Hamiltonian density, which we have already done. And now, see, it will be crucial to remember and always pay attention to the arguments of individual functions. So, what is this Hamiltonian? Let me first talk about the Lagrangian density. Lagrangian density we know is function of the field variables, then its partial derivatives with respect to each one of these parameters x, y, z and t, and the x, y, z, t, all these 4 variables themselves. Whereas, the Hamiltonian is function of the field variables eta, then remember pi sigma is now separated from the remaining partial derivatives. Pi sigma is actually connection to eta sigma dot, and remember, I have all these eta sigma comma mu, which contains eta sigma comma 0, which is exactly equal to eta sigma dot, but I also have eta sigma comma I. These are eta sigma I, these are partial derivatives of the field variable with respect to x, y and z. So, you see, the moment I made this definition for momentum density, I have already done some harm to the beauty of the Lagrangian formulation. That is, in the Lagrangian formulation, all these 4 variables x, y, z and t, they appeared on the same footing. In the equations, they appear symmetrically, okay, but not in the Hamiltonian dynamics. This is a problem. I will describe this in a moment. Okay. But remember, now you have Hamiltonian density, which is function of pi sigma. It is function of all the other partial derivatives of field variables with respect to all x, y and z, and then x, y, z, t, all of them. Okay. Now, let us start. If I want partial derivative of Hamiltonian density with respect to pi sigma, that is very simple, because you have pi sigma here. So, when you take a derivative with respect to pi sigma, I get eta sigma dot, and then pi sigma into eta sigma dot divided by partial derivative of eta sigma dot with respect to pi sigma, minus, now the Lagrangian depends on the pi sigma variable through here. So, it will be partial derivative of eta sigma I with respect to pi sigma. And then notice that this term here and this term here, they are actually exactly same, because partial derivative of L with respect to eta sigma dot is exactly equal to pi sigma. So, this term here will cancel and you are left with eta sigma dot. Okay. So, my first Hamiltonian equation, well, that looks like what I wanted it to be. What about the partial derivative of H with respect to eta sigma I? Now, remember, I have to take all the individual cases and check them. So, here what depends on here, pi sigma is an individual variable. Okay? This is a individual variable, but eta sigma depends on eta sigma comma I. Similarly, the Lagrangian depends on eta sigma I. Remember, this contains your eta sigma I, and it also depends through the eta sigma dot. So, I will write all of that. So, derivative of partial derivative of L with respect to eta sigma I and minus del L over del eta sigma dot and then partial derivative of eta sigma dot. This is just the chain rule application. Okay. And then again note that this term here cancels neatly with this term, giving you. So, partial derivative of H with respect to eta sigma I is just equal to minus of partial derivative of Lagrangian density with respect to eta sigma I. Fine. Similarly, check for the other variables. Partial derivative of H with respect to t will be equal to partial derivative of Lagrangian density with respect to t. Same thing for x, y, z, t we have already written here. Okay. Now, I am going to look for that second equation. So, for the second equation, let us take the partial derivative of Hamiltonian density with respect to pi sigma. Okay. This one I have already written. Let us take partial derivative of H with respect to eta sigma. Now, the expression here again, it is pi sigma multiplied by eta sigma dot with respect to eta sigma minus L depends on eta sigma directly and L depends on, so that is this term, and L depends on eta sigma through eta sigma dot. Okay. So, I will write that term too, and then these two terms here, this one and this one will cancel, because note that partial derivative of L with respect to eta sigma dot is nothing but pi sigma. Okay. So, this also comes out to be neatly the, but this is where the problem begins. You see, unlike the finite or discrete systems, the Lagrange's equation now is not simple. It also has the total derivatives not just with respect to t, but it has a total derivative with respect to x, y, z too. It is a, remember, I will explicitly, if you want, I will write there is a summation over mu implicit in this equation, because mu repeats here and here. Okay. So, now I have to put that back here. So, partial derivative of L with respect to eta sigma is nothing but minus of d by dt. So, this term is equal to summation over mu of the first term, because of summation over mu contains 4 terms. I will write the first term, which is with respect to mu is equal to 0, that is eta sigma dot. So, the first term is d by dt of partial of L with respect to eta sigma dot, and then you have 3 more terms here which I have written using summation convention. So, it is a d by dxi of partial derivative of L with respect to eta sigma comma I, fine. Now, this does not look like, because I know that the first term here is minus pi sigma dot, that is the definition, but now you have additional terms there. You see, this does not look like the particle dynamics. The Hamiltonian formulation for particle dynamics simply would have said pi 6 dot is equal to minus of partial derivative of h with respect to eta sigma. That is what I was expecting, but that is not what we get here. So, when I now take the other terms to the left hand side, and now look at this. This is just a differential operator. This is a differential operator operating on h. So, the differential operator I will write here is del over del eta sigma minus d by dxi and partial of del over something. Okay. So, in this case of course, I will write eta sigma comma I. Okay. And this is a operator, and that operator operates on your Hamiltonian density. I am going to name this operator as delta. So, delta eta sigma. In general, it is called as a functional derivative. So, I will, if I take functional derivative with eta sigma, it is partial with respect to eta sigma minus d by dxi partial with respect to eta sigma comma I. Okay. Remember, there is an implicit summation over I here. If I take a functional derivative with respect to pi sigma, all that happens is this term here, instead of eta sigma, you would have pi sigma, and what would you have here? That would be pi sigma comma I. Okay. So, this is a definition of the functional derivative with respect to a quantity. Fine. So, now I can write partial of the functional derivative of h with respect to eta sigma is minus pi sigma. Fine. Now, in this form, it does look like the discrete system equations, but does it have any more advantage? Probably not. Apart from making these equations look nice, the functional derivative has no particular significance in this Hamiltonian formulation. So, I will write the equations of motions together. Remember the first equation. So, this is the equation we just now derived. The first equation was in fact in the form of partial of Hamiltonian density with respect to pi sigma. Okay. And when will it become this? Because remember, your Hamiltonian is function of which quantities? It was eta sigma, it was pi sigma, then eta sigma comma I, where I takes values 1 to 3, and x mu. Now, if you write this functional derivative, that would be, so I will write equal to partial derivative of Hamiltonian density with respect to pi 6 plus its d by dxi and partial of Hamiltonian density with respect to pi sigma comma I. And you see, pi sigma comma I is not one of the independent arguments of the Hamiltonian, which means this will be 0. Okay. So, I can safely add this term and write partial derivative of h with respect to pi sigma as functional derivative of Hamiltonian density with respect to pi sigma. And now, there is the symmetry in the equations which we had seen in case of the particle dynamics. Okay. So, everything has been restored, but this is of course not enough. There is something more here. Look at the final expression. Total derivative of Hamiltonian density, will it be equal to partial derivative of Hamiltonian density with respect to time? That is the question. Remember, this holds for the total Hamiltonian. Will it also hold for the Hamiltonian density? Probably not, and there is a reason for it. It is not surprising at all. Look, what is your Hamiltonian density? Look at the expression for the stress energy tensor, your Hamiltonian density is in fact exactly equal to T00. Okay. So, your T mu nu here was partial of L with respect to eta sigma nu, eta sigma mu, and then minus L of L into delta mu nu, that is your T mu nu. Look at what happens to T00. T00 is when you put nu is equal to 0, mu is equal to 0. But the moment I put mu is equal to 0 and mu is equal to 0, it is the derivative with respect to time. That means, all that I get here is eta sigma dot, and this is also eta sigma dot. This is T00, but wait, that is exactly the definition of the Hamiltonian density. So, there this would be pi sigma into eta sigma dot minus L. Okay. So, your Hamiltonian density is in fact T00, but T00 conservation is, remember, through this equation here. In case of stress energy tensor, we have already done this, that the T00 component, which is energy density, will be conserved, or energy is a conserved quantity if the Hamiltonian or the Lagrangian does not depend on T. But that is a statement for the total energy conservation. What happens to the energy density? So, you have a system, that rod, and you look at small portion and look at the energy density there. What we are saying is that the total energy of the rod is a conserved quantity, but not of the small portion. What is happening there? The energy density, that means the energy in a small volume, is escaping through the boundaries, and this in fact is like a continuity statement. It is conservation theorem not for T00, but it is a conservation theorem for integral of T00. Okay? Right. And then T0 is a 3 vector, and the components of that are just the energy current vector or energy current flux vector. So, the energy passing through the surface per unit time per unit area is what we are looking at here, right. So, now I can write down the total derivative of the Hamiltonian density, because Hamiltonian density has been identified with T00 here. So, dH by dt is same as dt00 by dt, and that would in fact be equal to this. And then if the Lagrangian, so I will of course write this as in terms of Hamiltonian, partial derivative of Lagrangian density with respect to eta sigma I is minus of this bracket. Okay, so that minus sign will become plus here, and this also will become plus. So, I will write this in terms of Hamiltonian density, and now I have that statement that if Hamiltonian density is independent of time, then partial derivative of T00 is exactly equal to this quantity here. And remember, eventually the statement is the total energy which you obtain, or total Hamiltonian which you obtain by integrating this Hamiltonian over space volume, the entire space volume, is the quantity that is conserved. Okay, fine. Lastly, I will also try and see how Poisson brackets emerge. Even Poisson brackets will not provide us a great start as far as generalizing these theories to the modern theories are concerned. So, similar to the densities, remember the densities are problematic case here. So, if you take a function u which is function of eta sigma, pi sigma, I will add eta sigma I and also pi sigma I. Remember, the Hamiltonian is not function of this, but if you are taking arbitrary function, there is no harm in including terms like this. So, u is some sort of a density which depends on all these variables. And now you define capital U as integral of u over the space. Okay. So, u is the total quantity, small u is the density. And now, look at what happens to capital du by dt. This is what we always wanted, capital du by dt, that is integral, and now I can of course interchange the integration with respect to the space variables and the derivative with respect to time. And then when I take derivative of this du by dt, then of course I get all these terms, because all these field variables, the first 4 ones which I have written here, they depend on time t implicitly. Okay. So, you get del u by del eta sigma dot, and similarly of course all the other terms. And now, put everything together. Remember what we have here, this particular term here, this one here. Okay. What I will do is this, this is nothing but, so this term I am rewriting here as del u by eta sigma I d by dt of d eta sigma over dxi. Okay. Do integration by parts. What happens when you do integration by parts? The derivative d by dt will shift to the other variable. So, I am actually going to interchange d by dt and d by dx. So, first it will be derivative with respect to x and then the derivative with respect to time. Now, do the integration by parts, and then you get term like this, which is eta sigma dot, and this derivative operator of course will shift to the other term or other function in the integral. This also of course requires the surface term to be 0. So, which we will assume that for a given volume the surface terms are 0. Now, you put it back into the equation and notice that the functional derivative of u with respect to eta sigma is in fact what exactly appears here. So, this entire expression will in fact become functional derivative of u with respect to eta sigma into eta sigma dot, and functional derivative of u with respect to pi sigma into pi sigma dot. And then we have eta sigma dot. What is this? According to the Hamilton's equation now, eta sigma dot is nothing but partial of Hamiltonian density with respect to pi sigma. Fine. So, we will add that, and now look here. This has the structure of Poisson bracket, but it is under the integral sign. Okay. So, what I am going to do is, look, if I had a Poisson bracket of discrete system, then remember there was a summation over I, and then you have derivatives with respect to individual generalized coordinates and corresponding momentum. That summation is anyway going to become integral here, and I will write this as Poisson bracket of u comma h plus del u by del t. Now, this has come. So, the Poisson brackets have emerged from the Hamilton formulation like it did in case of finite or discrete systems, and not surprising. And this also immediately gives you the equation that we were looking for, which was dh by dt will be equal to del h del t. Here remember, this is the total Hamiltonian and not the Hamiltonian density, because capital H we are going to integrate Hamiltonian density times dV. Okay. Fine. So, everything now fits, and you get equations which are exactly similar to what you would get from the discrete systems. This is the way you can actually write down the Hamiltonian formulation and Poisson bracket formulation for even the continuum systems. Now, what is not nice about this is the fact that it does not treat the space variables and the time variable on the same footing. And why is that important? Because remember, when we generalize these theories, 2. So, as of now, while doing all this discussion, I never in fact talked about the relativistic covariance. Even though x and t are treated say on the same footing, there is no specific property that relates x and t variables together. They remain distinct from each other. Only thing is that in all the equations, they appear as if they are treated on the same footing, or they are treated exactly in the same way. T is not different from x. But when you go to relativistic field theories, and that of course is what you would do when you are trying to generalize these to the fundamental theories, you would talk about the relativistic field theories and then talk about quantizing those relativistic field theories. So, now in the Hamiltonian formulation, I do not have that facility anymore. So, it turns out that all the generalizations are done using the action principle and the Lagrangian formulation to more modern theories, and whose basis of course lies in the relativistic field theory. Okay. So, this is where I am going to now end this week. Remember, our focus was of course not in trying to understand various fields, field theories like relativistic field theory, or talking about the individual fields like electromagnetic field or gravity, but to just construct the framework in which these fields are treated, and that is exactly what we have done in this particular week. So, this sort of brings us to the end of the course, and remember the announcement which I made in the beginning of this week, that the last week is excluded from the final examination, but there is an assignment that you have to do. Okay? Assignment carries marks, remember. So, submit your assignment, but you need not, you can skip this portion for the final examination. All this while, in last 8 weeks, I have of course enjoyed making all these videos and talking to you people, and also getting your feedback through discussion forum and so on. And this is of course the first time I have made a course like this or offered a course like this, and I have immensely enjoyed it. I hope that you also have enjoyed this course, but do give me feedback, whether anything that I could do or could have done to improve this course.